Hello, I'm Tom Willemain, one of the co-founders of Smart Software, and today we're talking about the subject of automatic forecasting for time series demand projections. If you've been following our sequence of talks, you know that there are multiple methods used to predict future demand for an item. And if you have thousands or tens of thousands of items, that means that you have to make thousands or tens of thousands of choices about which technique to apply to which item. And we know that some items have very different behavior in terms of the demand patterns than other items. Some are basically level, sort of look like this. Some have trend, either up or down. And some have seasonality, so they're cyclic. And each of those different patterns requires a different technical approach, a different statistical forecasting method. So if you have, say, 10,000 items, that means you have 10,000 choices to make. So how do you do that in a sensible way? Let me suggest three alternatives, two of which are pretty stupid. One is you decide that you have a pet method, a favorite method, and you use it for all items. Well, that's an obvious loser, because if your pet method is the simplest method, say simple exponential smoothing, which works well with data that look like this, and your actual data are seasonal, then you're going to get poor results. So you can't just say, let's keep it simple, I have a favorite method, apply it to everything and hope for the best. So that's a loser. The second not so good idea is to understand that you do have choices to make and to go ahead and look at the history of the item's demand and make an informed decision about which choice to make. That's actually very expert behavior, but it doesn't scale well. You could probably have the patience and time to do that for a dozen items, and if that's all you have to worry about, then that's fine. But if you're in a mass production situation and you have 10,000 items, you just can't get the job done by making individual, informed, wise choices. So you have to turn this over to some sort of robotic mechanism called a computer program. And automatic forecasting is a procedure for doing that so that you will do it sensibly and get good accuracy and get the job done in time for the forecast to be useful to plug into your planning process. So that's our subject for today. And we'll talk about the automation of this selection of methods. Now, if we're going to make a choice of methods, then we have to have some criterion for deciding which method wins, which is the best one. And that choice, of course, can vary from SKU to SKU, from item to item. So the criterion that makes the most sense is to say, what's the typical error we would expect when we make a forecast of future demand? And we have to realize that usually we're making a forecast over a period of several time periods. We call that a forecast horizon. So for instance, you may require monthly forecasts, and you may require them over the next 12 months if you're doing annual demand planning. So there are 12 forecasts you have to make for each item, January, February, March, April, and so forth. So there are actually 12 different accuracy tests that you have to make. How do we do in January? How do we do in February when we're going 2 months into the future, 3 months, 4 months? And so the simple criterion that we use in our software for evaluating accuracy is to say, what's the size of the error, the difference between what we predict and what actually happens, averaged over the entire forecast horizon. Generally, the farther you go into the future, the more the world can throw contingencies at you, and the less accurate forecasts get. So the one month ahead forecasts tend to be a little more accurate than the 2 month and 3 month and 4 month. And if you take that entire set, say, of 12 monthly forecasts, you have 12 error figures, and we take the average over the 12 as a criterion for deciding which method works best for which item. It's a reasonable approach. And again, the error is just simply defined as the difference between the forecast and the actual value. And to eliminate the chance when you take averages that low errors, which will have a one sign, will be offset by high errors of the other sign, we take the absolute value. In other words, if you're low or high, if you're -5 or +5, we just call it a 5, so that the minuses and pluses can't cancel out. So that's what we're going to use as the forecast criterion. Now, how do we make the decision, given that criterion, of which method works best? Ultimately, the way you would decide to do this, if you have the time, is to try them all, wait for the year to pass, and then look back and see which one worked well. That's something that usually you don't have the luxury of time to do. You have to make a decision now about what you think will work best in the future. So you're sort of making a forecast about the forecasting method you need. So what we need to do in an automatic forecasting technique is to find a way to simulate the process of waiting for the year to elapse and being able to look back and see what happens. And that's a technique called holdout analysis. And let me show you a little bit of a picture to get that idea in your mind. Let's suppose this is time, and each of these little slots are observations. And so you might have, for instance, you want to forecast these last 4 quarterly values. Maybe this is quarterly data. So this is the next year. And you'd like to know what are the demands for this item in those slots. And for these, we have actual numbers. We know what those are, and that becomes the information on which we base the forecast for the following year. Now, what I just said is an impractical but very good way to do it if you had the time, is to try a method, fill in the forecast, see what happened here, and compute the errors. There'll be an error here, and another number here for the error, and another number, and you take the average of these, and that's a score for a particular method on a particular item. If you can't do that, then what we do is something else. We would take the history, this is the history of the demand, and this is the future. We will take the history and we break it into 2 pieces. We will take this that we will use to make the forecast, and this we will pretend we don't know. We call that a holdout sample. And we will only use some of the history. So we'll use this information to forecast what will happen then, and we already know the true answers. So we don't have to wait for the year to elapse before we can get an idea of how well a given method will work on a given item. We can take our history, hide some of it, forecast, then unhide it and compute the errors. So that's the technique we can use in software to make a decision in real time about what method should be applied to which item, and then we could just cycle on to the next item and the next and the next. And of course, if you don't have much history, this doesn't work very well. And so the longer the history you have, you're probably better off when doing this. So there's always a premium, an advantage to having more data, except to the point where some of the data is so old that it's from an obsolete business environment. And then it just becomes pollution instead of a positive. And you probably need to make a judgment about how far back you go with an item, because some of the stuff is from an irrelevant environment and doesn't apply now. So there's some discussion or thinking you have to do before you do the comparisons of methods, to think about what data are going to be used to evaluate the techniques that are competing for the chance to forecast a given item. And that involves some business judgment, but in general, if the world is fairly stable and the markets are not very volatile and not changing a lot, is to use as much of the past as you can, and then to hold out as much as you need to simulate the passage of time and to make a prediction about how a method will work with a given item. So that's the overall philosophy, or the way we set up our thinking about this problem. And what we'll do next is think about how you would actually execute this in terms of a computer program to do the grunt work. Now we'll talk about the way we actually execute the choice of a method for a given item. We call that a forecasting tournament, because we allow the various methods that might be useful to duke it out and to fight for the right to own that item and to make the forecast for that item. And this involves a purely empirical, very computational analysis of the demand data. So we'll imagine that you have, starting with the demand history of an item. So that's your empirical basis. This is the way the item has behaved over time. And then you have forecasting method number 1 and forecasting method number 2, and let's say there's 3. Forecasting method number 3. So those are all competitors to forecast a particular item. Demand history of item, let's say it's item number 7. So we take that demand history and we feed it into the calculations for method 1 and for method 2 and for method 3 in turn. And then what we have, as we said before, is we have separately held out some of the demand history. That's our so-called holdout data set. We're going to use that as the ground truth. This is what actually happened at the end of the demand history that we're using as input. And so this is going to be our ground truth, and we're going to make a set of forecasts. Forecast method number 1, and we have a set of forecasts for method number 2 and forecasts for method number 3. And each of these would be compared to provide us an estimate of the error that you would get using this method on item number 7. And likewise, we're going to be doing the same thing. Estimated error, we'll call this number 2. This is number 1. And we'll have the estimated error for method number 3. And this is the score that each of these methods gets. It's a forecast of the forecast error. And these are all competing. And we compare this and we pick the best, which is to say the lowest average error. And that determines which of these methods handles item 7. Then we move on to item 8 and item 9 and item 10. Basically, that's the way this works. There's a little bit of refinement because these methods actually have knobs or parameters in them, so they're variations of each method. But this is the big picture. Start with some of the demand history, hold out some to see the actual accuracy assessment. Try each of the methods on the demand history, make the forecasts, and compare them to the actuals. Compute a summary measure of error, the average absolute error, in other words, ignoring whether the sign is positive or negative, and then pick the best, and then move on to the next item, repeat the whole process. So this is very computationally expensive, but that doesn't matter anymore. It didn't even matter back in the mid-'80s when we invented this technique and first began selling it in software. So that is the overall architecture of a forecasting tournament. There is still a choice about which methods you're going to allow to compete, and of course you have to decide which items you care about forecasting, but those are easy choices to make. Now let's think a little bit about what happens at this last step, where we're actually computing the error estimates for each of the methods and picking the best. I've taken the time off camera to put together a little toy example of how that will work. So we're thinking here about making 3 forecasts. We're going to call them now plus 1, now plus 2, and now plus 3. So we're going 3 periods into the future. Whether those are 3 days, 3 weeks, 3 quarters, or 3 years, doesn't matter. It will be whatever your planning process requires. But here we have 3 forecasts. And here we have the actual values for this item. The next period beyond the history that we're using to compute the forecast would be a 50, and then the next one a 55, and the next one a 60. So you're seeing some sort of, it looks like there's a trend here, a positive trend. Now these numbers would come from the holdout data. We've hidden those from the calculations because we want to see if we can correctly predict what actually happened without cheating, without looking at it ahead of time. So here is the truth from the holdout data, and then a particular method would make forecasts, and this particular method forecasted a 48, and then a 51, and then a 63. So it was forecasting some sort of increasing demand. But how do we assess 48, 51, and 63 compared to the truth, which was 50, 55, and 60? Well, here's the error, which is the actual minus the forecast, or I'm sorry, the forecast, the actual minus the forecast. So the error in this case was plus 2. The actual was 2 above. In the second period into the future, the error was plus 4. In other words, if we took the forecast and added in the error, we would get the truth. So we take the forecast, and if we'd have just gone up 4, we would have hit it exactly. And in the third period, we actually overshot. We had a 63. If we had come 3 lower, we would have hit the truth of 60. So we have now 3 error figures, plus 2, plus 4, and minus 3. And what we need is a single number to describe, on average, what happens in this planning problem. We've got a 3-period forecast horizon. What's the average over 3? And we take the absolute error, which means we ignore the minus signs. So plus 2 stays as plus 2, plus 4 stays as plus 4, minus 3 becomes a plus 3. We don't let this subtract and make the total error seem smaller than it is. And so a 2, a 4, and a 3 average out to a 3-unit error for that method over the 3-period forecast horizon. And that would be the error estimate of which we would compute for each of the competing methods on this item. And of course, for the next item, we'd go through the same calculations. But when we look at these average errors, we obviously pick the one that is the lowest, and we say there's a match now. A particular method would, the winner of this tournament is the one we will assign to making the forecast for that item. And the next time we do this, maybe 6 months from now, we have a repeated planning exercise, we will recompute things. It's all zero-based. We don't say, well, this one worked well last time, so maybe we're just going to persist and use that technique on item 7. No, because the world may have changed, the demand pattern may have changed, and now the method that worked well 6 months ago is not the best thing to do now. And so this process just recomputes everything from the beginning, and in that way it adjusts to the changing business environment that you're dealing with. So let's stop for a minute and connect back to something that was mentioned in one of our earlier blogs. Let's be a little more specific about these anonymous method 1, method 2, and method 3. So let's replace these with actual techniques. So if you caught the video blog about exponential smoothing methods, you'll remember that one of them was called simple or single exponential smoothing, another was called Holt's, and another was called Winters. So simple exponential smoothing is for data series that are basically flat. Holt's was for data series that have a trend, and Winters was for data series that are seasonal and have a cyclicity to them. So the given data series will be closer to one of these, and that should play out in the calculations. And you might think, well, again, if you're willing to take the time to look at the series, that you could just classify them and make the choice yourself. We've talked about that that's inefficient. It doesn't scale up to large problems. But there's another issue here that makes the calculation a good idea, besides its ability to scale up and do a lot of work in a short period of time. And that is that real data series may not be unambiguously in one of these three camps. So let me draw a picture that might represent something like that. Let's suppose that we're looking at sales versus time. And if we had a data series that looked something like this, we would pretty clearly say that there's no trend and no seasonality. So this particular type of method, simple or single exponential smoothing, would be the one that would give us the most accuracy. However, suppose that what the actual series looks like is more something like this. Now, that's ambiguous. You could say it looks like there was a period of flatness and now it's gone into a period of trend. And these ambiguous pictures unfortunately turn up a lot in real life. Maybe because the world is dynamic and the characteristics of the market can change over time. And so actually doing this by eye works best when the world is simple, and the world isn't always simple. So the calculations allow us to just say, maybe what we're seeing here is the kind of floating that just goes from one level to another, and we still want some sort of a flat, level-based, simple exponential smoothing to handle the problem. Or maybe we'd make a big mistake if we didn't use a trend. Well, both of these approaches can be calculated here, and we'll see which one actually works for that item. So we don't have to make the eyeball judgment, and sometimes it's difficult even for someone who's seen many time series to make a clear call. This is the best method, that's the best method. So this objective data-based approach has certain advantages even when you think you're an expert and you think you're going to see a clear picture and you're going to be comfortable making a call about which method to use. Not always. And so that's another reason to go to a forecast tournament instead of making a one-by-one gut call about which method to use. So stay patient, we're on the final leg here. The next level down is to talk about the details of the holdout analysis, because what you've seen so far makes it seem as if there's just the near future. There's a history and then there's the near future. We hold out the most recent data, we do that once. But actually we don't do that. There's more computation involved. We sweep repeatedly through the history. So let me show you a cartoon of how that works. So imagine this is our data, and we're going to divide it into a holdout section, which we hide, and we'll call that a history section, which we use. So we will use the data in here. This is our demand data. And we will temporarily split them here. And suppose we have a forecast horizon of 2 periods. So we actually have all this data that we're not using at first. We're even holding out some of the holdout. But we're saying, let's make a forecast, well, let's say 3 periods ahead. And we use this much data and we forecast 3 periods ahead. And then we see which of the methods does well there. Okay, so we'll have an error for method 1, method 2, method 3. And then we'll do it again, starting 1 period further. So we'll now use 1 more period of data, and we'll look at the next 3, and we'll keep these in reserve. So we have now looked at 2 times we've looked 1 period ahead, 2 times we've looked 2 periods ahead, and 2 times we've looked 3 periods ahead. So we're going to have multiple exposures to how it works out over the next 3 periods, and we can average the averages to get a more statistically stable ranking of the competing methods. So we keep doing that. We keep sliding this technique. We use more of the data. We look 3 periods ahead, and we're keeping this for future use. And we keep doing this, and this is called, not surprisingly, a sliding simulation. It's sliding because we're sliding the amount of history we use to get more experience with a 1 step ahead forecast and a 2 and a 3. And it's a simulation because we're pretending as if we're actually in real time making a forecast and waiting to see what happens. We're just skipping the waiting part. We're uncovering the holdout data to see the actual demand and making our error calculations. So we're sliding along, and this gives us, now we have at this point 3 values for the 1 step ahead error, 3 values for the 2 step, 3 values for the 3 steps, so we can average all those and get 2 advantages. One is that that's more statistically stable. The average of 3 numbers is a more accurate estimate of what's happening than the average of 1. But also, we're allowing for the fact that the data can be changing over time, and we're letting that happen. We're simulating the actual dynamics of the market so that we get a more realistic set of numbers. So, for instance, if we had a situation where the demand history was doing this, and we cut it here, and then all of a sudden something happened. Maybe we had a tremendous marketing campaign, and the future data was like this. The performance of a forecast like that would be pretty poor. But if we keep looking and the method adjusts, we're going to get a different idea of how a level method that's adjustable, like simple exponential smoothing, would perform in a volatile situation. So we don't do the holdout analysis once. We do repeated sweeps, each one a little bit using more and more of the data. And finally we run out of gas here. We don't have any, and the final simulation we would just be holding out a single data point, and we would not be able to do a 2-step and a 3-step ahead forecast. But we squeeze everything we can out of the holdout data, so we have one more data point to see how a 1-step ahead forecast would work. So the computation, which looked big before, because we have repeated sweeps using each method on the same data, is actually a bigger computational burden, because we're changing which data we feed into the methods and recalculating the errors going farther and farther into the future. But that provides us with a more comprehensive assessment of error. And then there's one more computational enhancement that also makes this more intensive a calculation. And that is to realize that each of these methods that we're evaluating is really a family of similar, sister methods. For instance, with single exponential smoothing, there's a single weighting factor which says basically how much do we discount the oldest data and give more attention to the newest data coming in from the market. So that's a weighting factor that can go from 0 to 1. And the best performance of that method may vary a lot depending on how we discount old data compared to new data. So when we talk about a method like single exponential smoothing, we actually may talk about multiple representations of that method. So single exponential smoothing with alpha equals 0.1 is a competitor, but single with alpha equals 0.5 is another competitor that pays more attention to what's happening now and less to what happened in the past. And single with alpha equals 0.9 is paying a lot of attention to what's happening now and not using much memory of where the demand was in the past. And we can start making plots like this. Here is the average error and how it depends on this choice of the alpha parameter. This goes between 0 and 1. We might be trying 0.1, 0.5, and 0.9. And suppose we get a result like this. It looks like the best way to tune this method is to put alpha near 0.5, but we go even farther and we say maybe it's even better to look here. Let's call that 0.68, and we try a fourth value. So with every method, we're trying 4 variants of the method with different parameter settings, and then we're doing multiple passes through the holdout data. That involves a huge number of machine cycles, a lot of computing, but the hardware today can handle that in the blink of an eye. So it works, and it doesn't take too long to get your answers. And it certainly beats trying to make guesses or pick a single method or deciding to handcraft the forecast one at a time. So to summarize the way the automatic forecasting tournament works, there are basically 3 steps. You look at a version of each method over the holdout data, and then you pick the best version of that method. So that's the best you can do with, say, method 1, single exponential smoothing. And then you do the same search over the possible variants of another method, like Winter's method. That has different ways of discounting the old data relative to the new data. You find the best tweak of Winter's method for this item. So you get the best of the best for one, you get the best of the best for the others, and those are sort of local champions, and they go to the final playoff round where the final tournament decides the overall winner. And that is a very effective, it's been proven over decades to be a very effective and efficient way to automatically manage all the grinding part of statistical forecasting for demand. And then there's a final touch, which is to say there may be more information available to your brain than is in the historical record. For instance, you may know that your competitor in Manitoba is going out of business, and so you're going to grab a share of that business. That's not in the historical record. It's what's going to happen next month. And so we allow in the software for the statistical basis of a forecast to be modified by market intelligence and by expert judgment. So that, for instance, if you know that you're going to run a marketing campaign that in the past has been successful, you might push up your forecast. Or if you expect that you're going to have a plant closure because you've had a fire, then you could push down the forecasts. And that combination of letting the computer grind the problem to death, try multiple methods, tweak each one to its best performance, and then pick the best of the best, and that's an empirical, fact-based starting point for the forecasting. And then having a meeting where you bring in your team, your salespeople, your marketing people, and you blend in their judgment and their intelligence, their knowledge of what's happening next in their markets. That combination ultimately produces an effective and realistic demand planning process.